Good afternoon, everybody. Welcome to this week Autonomy Talks. This week is a great pleasure to have a talk from Pol Duhr. Short bio, Pol did his bachelor and master's in mechanical engineering at ETH Zürich in 2015 and 2018, respectively. Today he's a PhD candidate in Chris Saunders' group at the Institute for Dynamic Systems and Control. And he works on application of optimization and control algorithms to energy management for hybrid electric race cars. Some fun side notes about Pol. We shared an office together for many months, and he's really a saint because he's sharing an office with all Italian-speaking, close to all Italian-speaking colleagues. So it's really not the most quiet office of IDSC, and he's keeping up and enjoying every day. And also he speaks Italian really well now. So he's really learning quickly. So that's a fun story about Pol. So today we'll talk about energy management optimization for the Formula One race cars. And I really look forward to hearing this. Go, Pol.
Thank you for the kind introduction, Joelle, and don't be afraid, everybody. The presentation will be in English, not in Italian. So without further ado, let's start. As the title suggests, today we will talk about Formula One racing. And if you look at Formula One cars over the past 30 years, so here I've put pictures from two examples, one from 1990 and one from 2 years ago, the cars have become a lot more complex. Not only in terms of their aerodynamics, which means more grip, and therefore the cars have become faster, but also in terms of the steering wheels. So if you look at 30 years ago, those were simple items with basically two buttons, one for the radio and one for the pit speed limiter, whereas today you have a lot of buttons and switches on the steering wheel, a screen, LED lights, so the whole thing is a lot more complicated. And partly this is due to the fact that in between, Formula One cars have moved from a powertrain that featured a simple, large, naturally aspirated internal combustion engine to a complex hybridized power unit. So now we have still an internal combustion engine, but it is accompanied by an energy recuperation system, an energy recovery system, and together these form the so-called hybrid electric power unit. So let's have a look at it in greater detail. At the core of the power unit still sits the internal combustion engine, which is now downsized and turbocharged. It's a V6 with 1.6 liters of displacement volume, and it provides us with the power P engine. It is supplemented by two electric motor generator units, that's what the MGU stands for, which are connected to a battery. The first one is called the MGU-K, K for kinetic, and it is directly connected to the engine's crankshaft, and it can serve for electric boosting under acceleration and electric recuperation under part load and under braking. The second electric motor is called the MGU-H, where H stands for heat, and it is connected to the turbocharger, and it can recuperate waste heat from the exhaust gases and also drive the turbocharger to eliminate turbo lag during transients. Then we have very powerful friction brakes on the car in order to slow down before the corners because of the high speeds that we achieve. And the whole power is channeled through an 8-speed sequential gearbox. So we have gears 1 to 8, and the gearbox must be actuated by the driver with little levers on the steering wheel. So we cannot have a fully automated gearbox. Now, the key performance indicator for this powertrain used in Formula One racing is not acceleration or top speed or fuel consumption, it's lap time. So Formula One races take place on closed circuits, and lap time is the time it takes to cover one lap of such a circuit. Now, there are several regulations in place that make it more difficult to achieve a low lap time. First of all, the fuel consumption is limited to 110 kilograms per race. So refueling during pit stops is not allowed anymore. Moreover, the fuel mass flow is limited to 100 kilograms per hour. The battery size is limited to a usable size of 4 megajoule, and the power of the MGU-K can range from minus 120 kilowatts during recuperation to plus 120 kilowatts. Moreover, we have a limit on the electric boosting energy that goes from the battery to the MGU-K, 4 megajoules per lap, and recuperation that goes from the MGU-K to battery, 2 megajoules per lap. And already here you can see 4 megajoules and 2 megajoules. That doesn't square up. So a lot of recuperation will have to come from the MGU-H, which is not limited. And therefore the MGU-H is a crucial component of the power unit. Now, the regulations limit the available energy, as you can see, and this is done in order to promote an efficient operation of the power unit. And therefore, because the driver, although he has a lot of buttons on the steering wheel, he cannot coordinate all the actuators by himself. We need a sophisticated energy management that decides on the internal combustion engine power and the power of the two electric motors. Now here I've plotted the velocity, a typical velocity profile of a Formula One car over a lap, and in dotted line, the maximum velocity profile that is achievable by the vehicle dynamics. So basically the grip and the adherence of the tires. So here you can see velocity decreases in the braking zones. Then we have a local minimum in the corner. Then we accelerate out of the corner again. Now we can identify two regions. The first are the so-called grip limited regions. So that's under braking and in the corner where we are at the grip limit of the tire. And there, because we have a driver in the car and he should drive the car alone and unaided, traction control is forbidden, which means that the energy management must provide exactly the propulsive power that is required by the driver who presses the accelerator pedal. So the energy management can only decide on how to split it up between the internal combustion engine and the electric motor MGU-K. On the other hand, on the straights, the energy management gains an additional degree of freedom. Here we are power limited, so the wheels are pointing straight. We could go as fast as we like until the next braking zone, and only the propulsive power that we put limits the velocity that we can achieve. And here we can do thrust controls, so the energy management can decide on how much power to provide in total and how to split it up between the actuators. What is now the difficulty in terms of energy management? If you look at this simple schematic of a circuit, and we imagine that now the driver drives at full throttle on the straight, consuming 300 grams of fuel, and then he goes through the corner and uses 120 grams of fuel there, and he repeats this on this symmetric lap on the other straight and corner, then at maximum engine power, he would consume 840 grams of fuel. Now, and this is the question that arises in Formula One, since fuel energy and so on are limited. What if the fuel is limited to 600 grams per lap? How should we split up the fuel consumption then? Should we reduce a bit on this straight, go slower through the corner in order to save a little bit there? In the same fashion on each straight or differently? So that's not a trivial question to answer, which leads us to the energy management problem, and let's have a brief look at the related research. So given that we have this duality between the operation in the corners, in the grip limited regions, and on the straights in the power limited regions, there are two large research areas that are related to this. First of all, the minimum fuel power split problem, which deals with the control of conventional hybrid electric vehicles, such as this Toyota Prius, where the power request is given at all times by the driver who drives the car, and the energy management has to split it up between the internal combustion engine and the electric motors. On the other hand, we have the field of minimum fuel thrust control, which emerged with autonomous vehicles and also with adaptive cruise control, where the controller can also set the vehicle's velocity and thereby the propulsive power that is required. And our research is a bit in between the two. We call it minimum lap time energy management, and we have both of these aspects. We encounter them during a lap. Now, in this talk, we are dealing with non-causal offline optimization. We have a given race circuit, and we want to find out what would be the best possible energy management strategy along such a lap. If we look in literature, people have applied methods such as dynamic programming, convex optimization, then optimal control theory, mostly in the form of Pontryagin minimum principle, then also mixed integer linear programming or nonlinear optimization. In our group, in this field, the energy management problem was solved with convex optimization, and also PMP was applied to obtain an optimal control policy. But so far, the gearbox and the gear shifts were not considered. And this limited us to models that do not depend on the engine speed, because as you have seen on the schematic, the gearbox links the vehicle or the velocity of the vehicle to the engine speed. And if we don't consider it, we cannot have models that depend on the engine speed, which is quite restricting. Now, if we would like to consider this, then we can again look at literature. And in this field, people have devised special iterative algorithms that combine convex optimization, dynamic programming, and or PMP to take into account the gear shifts and also the engine on-off, so binary or integer decision variables. Now, in this talk, we are going to leverage the approaches and results that were obtained previously in our group, and also take inspiration from algorithms of this kind in order to come up with the joint optimization of the energy management and gear shift strategy. Specifically, we are going to combine convex optimization, Pontryagin minimum principle, and dynamic programming in order to do so. What are the questions that we would like to answer or have a look at in this talk? Now, as we shall see, given that the engine speed has an impact on the achievable propulsive power and also on the electric recuperation capabilities, the questions that pose themselves are, first, what are the interactions between the optimal energy management and the optimal gear selection? How are they depending on each other? Are there trends that we can observe? And then what is the suboptimality of a simple heuristic gear shift rule that would model the driver's behavior in practice? So I've told you that in the car, it's the driver who changes the gears. So the question poses itself, how much lap time do we lose when the gear shifts are a little bit suboptimal? We will do model-based optimization. So we will have a numerical optimization routine. We will look at one lap on a given racetrack, and we want to minimize lap time. And it's model-based because the optimization routine deals with a power unit model and the parameters of the specific power unit, and also a longitudinal dynamics model of the car. The inputs are the consumption targets, which are the fuel consumption for the lap, and then by how much we want to charge or discharge the battery. Makes sense to consider these as inputs because these are strategy parameters that the driver and his race engineer can define and set on the steering wheel during the race. Then here we have racetrack data in terms of a maximum velocity profile. And the output will be the optimal solution, so an optimized velocity profile, the gear selection trajectory along the lap, and then the power trajectories of the different components and the energy consumption as a function of the track position S. So without further ado, let's jump into the modeling part. Because it's model-based optimization, first we need a model of the power unit. Here I've drawn a schematic of the power flows that we have in the vehicle. And I want to focus here on two specific things. First of all, here we have the battery, and the power balance, or the power that is drawn from the battery, is the sum of the electrical power going to the MGU-K and the power going to the MGU-H, so the two electric motors, plus a small auxiliary power for electrical auxiliaries. These power flows can also be negative or in the other direction, then the battery is recharged. And power can be transferred freely between the two MGUs.
Oh, sorry for interrupting, but can you explain it? It's not clear to me how you recover energy from the heating.
Yeah. So it's mounted on we have the turbine driven by the exhaust gases, and this MGU-H motor generator sits on the turbocharger shaft.
Oh,
so
from the turbine. Essentially, you from the turbine, not from the heat.
Exactly, from the, yeah, it's like heat extracted.
Okay.
Yeah, exactly. And then on the other hand here, we have the power that goes to the wheels. So the total power of the power unit is the engine power plus the MGU-K power. That's what goes to the wheels. And then we modeled wheel slip with the linear wheel slip model. So this is a small loss coefficient. And the propulsive power at the wheels is the power coming from the power unit minus the braking power. Now we will go through the different components of the entire powertrain step by step. And we start with the power transmission, so the gearbox. As mentioned before, engine and MGU-K are coupled together by a set of gears. Then we have the clutch, the gearbox, a differential with a final drive, and the wheels. In this project, we defined an overall transmission ratio between the engine speed and the vehicle speed V, and it's called gamma G. And we have one large gamma associated to each gear between 1 and 8. And what we also take into account are the engine speed limits. So we have a lower limit that is basically set by drivability considerations, and an upper limit on the engine speed that comes from the regulations, and that's 15,000 revolutions per minute. Moreover, what we see here, we have this fixed gear ratio between the MGU-K and the engine. So the MGU-K rotational speed is directly proportional to the engine speed. If we then go on with the longitudinal dynamics, we model them in, it's a one-dimensional model. So we have talked about the propulsive power that drives the car. And in terms of resistive power, we model the aerodynamic drag, which becomes very substantial at the high speeds that a Formula One car achieves. And then we have the rolling friction. And also if the car, for instance, drives uphill like drawn here, we project the hill forces, so the gravity component in the direction of the movement. The car's velocity is denoted by V, and we have the classic kinetic energy formula, and then the kinetic energy evolves according to the propulsive power minus the resistive power. For the lateral dynamics, we don't want to do a vehicle dynamics optimization here, so we don't model them, but we condense them into a constraint on the longitudinal dynamics. You have already seen before such a maximum velocity profile. This can be obtained with a detailed simulation of the lateral dynamics or measured on the track using GPS data. And we constrain the kinetic energy such that the velocity is always below or at this maximum velocity profile. And this must hold along the whole lap. So that's how we take into account the lateral vehicle dynamics and decouple the energy management problem from the vehicle dynamics problem. Next, we go to the engine and the turbocharger. So first of all, the fuel that flows into the engine is limited by the technical regulations of the FIA, which is the governing body. And it's limited to this ramp followed by a constant value of 100 kilograms per hour, depending on the engine speed. Then the fuel power that goes into the engine is proportional to the fuel mass flow times the heating value of the fuel. Now this will be important for the gearshift strategy, because if we do an upshift at a certain point and we drop down in the revolutions of the engine, then it might be that we are very limited by the fuel flow limit and not able to put a lot of propulsive power. For the engine model, so the engine power, we model it as an efficiency times the fuel power plus a friction component and a pumping power component, more on which in a minute. The engine efficiency and the friction are both engine speed dependent, and we did quadratic fits as a function of the engine speed, both for the efficiency and the friction. So the dots are measurement data from the car. There is quite a lot of spread because of the low level actuation of the engine, but the trend is approximately quadratic. We also validated this model along a portion of a lap, and the errors are acceptable for our purposes. So we capture the important trends such that, for example, the friction power becomes more important towards higher revolutions. It's negative, so here the magnitude increases, and also after a certain point, the efficiency of the engine decreases again. Now, for this pumping power term, you have drawn a schematic of the air path of the engine. And if we follow the air, it gets compressed by the compressor, goes through an intercooler, gets cooled down. Then we have the intake manifold plenum. and then it gets sucked into the engine, where it mixes, where the fuel is injected and the combustion takes place. Then it goes through the exhaust manifold, and the exhaust gases drive the turbine, which drives the compressor. Now the engine can be seen as a volumetric pump, which pumps air from this intake manifold reservoir to the exhaust manifold reservoir with their associated pressures PIM and PEM. And that's what this pumping power term takes into account. And it depends on the engine speed and the fuel power, and also on the wastegate position. The wastegate is an actuator that sits close to the turbine, and it's basically a bypass of the turbine. And so if we open the wastegate, we increase, let's say, the open area for the exhaust gases with this additional path, and therefore the exhaust manifold pressure drops because there's less back pressure. So here we can see for a certain total mass flow, if we open the wastegate, the exhaust manifold pressure here on the y-axis drops. Therefore, we then have a larger pressure gradient from the intake to the exhaust, and the pumping power of the engine, this contribution increases. So if we open the wastegate, engine power increases. We derived a simplified model for this pumping power effect from first principle. You can see it's quite a simple formula with the engine speed, the wastegate position, and the fuel power. Also here, the validation showed that the error is quite small and acceptable for our purposes. Now we go on with the first of the electric motors, the MGU-H, which is connected to the turbocharger. And as you can see, it sits on the shaft, either behind the turbine or between compressor and turbine, but on this shaft. And we assume that the MGU-H is only operated in generator mode. So all the power that comes from the turbine and is not used up by the compressor to compress the intake air can be recuperated by the electric generator. We neglect the small transients at the corner exits where the MGU-H speeds up this shaft in order to cover the turbo lag. The mechanical MGU-H power can be shown to be roughly proportional to the fuel power that goes into the engine with an efficiency coefficient. This one is also engine speed dependent, and with a high fidelity simulation of the whole air path, we evaluated it for various engine speeds as what is left between turbine and compressor power divided by the fuel power. And you can see there's a certain trend. We fitted this spline, and it increases towards higher engine speeds. Also here, the wastegate plays a role. We define a wastegate position between -1 and 0. -1 corresponding to the closed position, where we get negative MGU-H power, so recuperation. And 0 is the open position. And you can see that when we open the wastegate, the turbine naturally produces less power because the exhaust gases bypass the turbine. And then the MGU-H recuperation drops to 0. So a couple of observations are in order here. There are trade-offs. So when we open the wastegate, we get a small increase in engine power due to this pumping term that we discussed on the previous slide. But the MGU-H recuperation drops to 0. So we have less electrical recuperation. Also, in terms of engine speed, we have a trade-off towards higher engine speeds. The engine efficiency decreases because the friction becomes more important, and also the efficiency decreases. But we get more MGU-H recuperation because here you can see that this recuperation efficiency increases towards higher engine speeds. So bear in mind those trade-offs for the later part of the presentation. We will come back to them. Finally, the second electric motor, the MGU-K, its mechanical power is constrained by its maximum achievable torque. And so here also the MGU-K rotational speed enters into these power limits. And then its electrical power is basically constrained by the FIA technical regulations. That's the plus minus 120 kilowatts limit. And this leads to a constraint on the electrical power. Then we fitted a quadratic loss model to relate the electrical power that goes from or to the battery to the mechanical power. And you can see that it's basically a set of parabolas for different rotational speeds. Also here, the fit is sufficiently accurate for our purposes as the validation for a few selected data points provided by the manufacturer showed. We apply a similar quadratic loss formulation also for the MGU-H electrical power. So that's it for the modeling components. Now we have had a detailed look at all the components. Next, we are going to devise the optimization methodology to solve the minimum lap time problem. So this is not to scare you, but it's just a summary of all the equations that we have seen before for the inputs and constraints, then the gearbox equations basically, and the states of our model. We have the kinetic energy, then we have the fuel consumption, which is just an open integration of the fuel power. Then the battery state of energy, which evolves with the power drawn from the battery. And then these boosting and recuperation quantities, which I will not discuss in detail here. Finally, the position on the racetrack, which evolves as a function of the velocity. Now, what are the initial conditions and terminal constraints to our optimization problem? For the position, we want to drive one entire lap on the racetrack. So we start at position 0 at the start line. And after one lap, we have covered a distance large S. So that's our terminal constraint. For the fuel, we just monitor we integrate the fuel consumption. So we start at 0 and we set a target fuel consumption. And in the end, we want to have consumed at most this target fuel consumption. For the battery, we assume that it has got an initial state of charge of EB init. And then we set a charge or discharge parameter. So if this is positive, we want to charge the battery and in the end up with at least EB init plus delta EB. And if it's negative, we can discharge the battery by this quantity. And the battery must stay within the bounds of its finite size. Finally, boosting and recuperation, limited to the 4 megajoules and the 2 megajoules. What is the lap time optimization problem? Well, lap time minimization, if we denote by large T the lap time, it's minimize 0 to T of dt subject to the state dynamics, so the position, the velocity, and so on, and the state and input constraints shown on the previous slide. And herein, as opposed to many other problems that were solved for hybrid electric vehicles, the velocity V is an optimization variable because it's directly related, of course, to the lap time. Ideally, we would like to optimize everything at once. So, but there are several issues with this. First of all, relationships like the engine speed as equal to transmission ratio times velocity, those are not convex because this is an optimization variable and this one as well. So that's a non-convex relationship. And also terms like efficiency as a function of engine speed times the fuel power and so on. So that makes it already difficult. And second of all, we have the integer variables. So the gearshift decision, which is basically between numbers between 1 and 8 different gears. And this would lead to a mixed integer nonlinear program, which is computationally very expensive and can have convergence and optimality issues or comes without optimality guarantees, global optimality guarantees. Our proposed solution to reduce the computational time, first and foremost, is an iterative scheme where we separate the optimization of the integer and the continuous variables. So if you look at the proposed iterative scheme, I'm going to walk through it step by step. Let's assume we have an initial guess for the gearshift profile and also an initial guess for the velocity profile along the lap. Then the engine speed would be given by this relationship at each point on the track. And we could pre-compute all the engine speed dependent parameters and use these in the energy management problem for the continuous variables. So all the power flows, the energy integration and so on, all that will be solved in here. And then once we have done that, we use the obtained velocity and the power inputs as well as the co-state variables, which we'll see in a moment, to optimize the gears. Then we get a new gear shift profile and also a new velocity profile. And we do the same thing again. And we walk through this until we converge. So until the gear selection and also velocity profile and so on don't change anymore. And we get the optimal gear shift strategy, the velocity profile, and the energy and power trajectories along the lap. Now, what we are going to look at next is how to solve these two sub-problems. So first of all, energy management via convex optimization. Here we assume that we have a gear shift profile, G, and a velocity profile, V, along the lap. And this means that all the terms depending on omega E, we can treat them as parameters. So omega E, given by our relationship, means that we can pre-compute all these efficiency, friction terms, the coefficients in the pumping power, and so on. And then I'm not going to describe this in detail here because it would take too long, but we can convert the whole problem to space domain using or introducing the lethargy, which is 1 over the velocity. We write the objective and also all the state equations and so on in space domain, so with the path variable S. And then introduce convex approximations and relaxations, discretize the whole thing with Euler forward. And finally, we end up with a second order cone program, which is the convex optimization problem and can be solved with global optimality guarantees and also with reasonable computational time. Second, so now we know how to do this. Remains the question, how do we do the gear shift optimization? We do this with dynamic programming and based on Pontryagin minimum principle. So as already seen before, we want to minimize the lap time t subject to the dynamics of the differential states x and the state and input constraints. The optimal control inputs according to the minimum principle are the ones that minimize the Hamiltonian H along the optimal state trajectory, and the Hamiltonian consists of the stage cost function, which in this case is simply 1 because we integrate dt, plus the co-state variable times the state dynamics, so the function f. And then the optimal input is the one that minimizes the Hamiltonian along the state trajectories. Our states, or the relevant states for this consideration, are kinetic energy, fuel, battery, boosting, and recuperation. And they have the associated co-state variables, which we denote by lambda. The, let's say, consumption co-state variables, so fuel, battery, ES to K and K to ES, these can be shown to be constant along the lap. And then the trajectory, the kinetic co-state variable, the one associated with the kinetic energy, is a trajectory, position-dependent trajectory. I've plotted it here under the velocity profile. You can see it has a peculiar shape. Its magnitude is always the largest at the beginning of a straight, so when we leave the grip-limited region. And this indicates that there, a small increase in kinetic energy would be most effective to reduce lap time. Whereas towards the end of the straight, when we already travel at a high velocity, a small or the same increase in kinetic energy would not have a large impact on lap time. Now, next, we construct the control Hamiltonian with the state equations. So it's basically kinetic co-state times propulsive power. These do not depend directly on the inputs, plus fuel co-state times fuel power. Then we have the battery part, the ES to K part, and the K to ES part. Now for the gearshift optimization, we assume that from the previous iteration of the convex energy management problem, we have the velocity profile V bar and the co-state variables at our disposal, which means that for each possible gear choice G at a certain track location, we can compute the engine speed that would result with this gear choice as gamma G times the velocity. Now, following the paradigm that we have these power limited and grip limited regions, we distinguish two cases. So in power limited, we have seen that propulsive power can be decided freely by the energy management. And we have, let's say, translated this into our gearshift optimization. So we take from the convex optimization as inputs the fuel power, the MGU-K power, and the wastegate position. Now, if we can select the gear, the given track index, for given fuel power, for different gears, different engine power is going to result, because the efficiency and so on are dependent on the engine speed. So different gears means different possible engine speeds, and therefore also different possible engine powers. Moreover, the MGU-H recuperation efficiency also depends on the gear choice. So does the MGU-K electrical power, and also the engine speed dependent fuel and MGU-K limits. And so we construct, I call it a pseudo-Hamiltonian, which depends on the gear choice and involves all these different components in dependence of the gear choice and the parameters that we recycled from the previous iteration of convex optimization. Then in grip limited regions, so in the corners, we saw that the power request has to be respected. And again, we translated this into our optimization scheme. So we take from the convex optimization fuel power and wastegate position and the propulsive power. Now we say, regardless of the gear we choose in the end, this propulsive power in the corner needs to be fulfilled to drive exactly at the grip limit. So if I change the gear, the engine, or depending on the gear I choose, the engine speed is different, therefore also the engine power is different. Therefore, the required MGU-K power to arrive exactly at P propulsive depends on the gear choice. And so do also some other components, and then we formulate this pseudo-Hamiltonian for the grip limited regions. You can see that there the term lambda kin times P propulsive doesn't appear anymore, because P propulsive is taken as given. So we can't influence it with the gear selection. Finally, we cast the whole thing into this gearshift optimization routine, which we solve with dynamic programming. Here it's already in spatial discretization. We define a stage cost function C, which is equal in power limited regions to this power limited pseudo-Hamiltonian, and in grip limited to this grip limited pseudo-Hamiltonian. And they depend on the gear choice. And then we want to optimize the whole gearshift trajectory along the lap. We have one input, which is the sequential gearshift command. So -1, we downshift one gear, 0 remain in the gear, 1 do an upshift. We have as a state G the current gear selected. So the next gear, the gear at the next step will be G plus the input. 8 gear choices available. Then we consider the engine speed constraints. So when we are traveling at 300 kilometers per hour, we can't go into first gear because then everything would break. So that's also considered. And as you would also do in your normal car on the street, we don't downshift under acceleration, and we don't upshift when we are braking or decelerating. So now we have seen how we can solve the gearshift optimization problem, and basically the iterative optimization scheme is complete. So it's time to look at some results. We are going to have a look at a small case study conducted on the for the case of the Bahrain International Circuit, which will host the Formula 1 Grand Prix in a couple of weeks. It's a nice racetrack in Bahrain. We have discretized it with a 5 meters spatial discretization. And just for reference, the computational time with the presented algorithm is in the range of 90 seconds to optimize an entire lap. We are going to look at some convergence metrics. So because a lot of things can potentially vary between iterations, we want to see if we actually converge. We are then looking at a case study for 2 different battery consumption targets. So one charge sustained case, where in the end the delta is 0, so we end up at the same battery state of charge than we started the lap with, and then also strong discharge case where we can use 2 megajoules of battery energy along the lap. So in the end, we have 2 megajoules less energy in the battery than at the start. Finally, we are going to discuss the suboptimality of a heuristic gearshift rule. Regarding the convergence metric, one intuitive thing to look at is how does the lap time change between iterations. And there we see that after a few iterations, it basically stabilizes and stays at a certain lap time. Then another thing that can change in each iteration of our iterative scheme is the gearshift profile. So here we have plotted the number of discretization indices with a different gear than in the previous iteration. So if I look at one track location between iterations, did the gear change or not? And we can see that as iterations proceed, this came down to 0. Then here for the profiles, so the velocity, which is the trajectory along the entire lap, and also this kinetic energy trajectory, which is used in the Hamiltonian, we have had a look at the average variation. And also there we can see that it becomes negligibly small after a few iterations. And also the other constant co-state variables converge to a certain value. So we saw that lap time, the gear shifts, the velocity profile, and the co-state variables converge. And from experience, we have seen that we can terminate after 10 iterations in most cases. Next, the small case study for the 2 battery charge or discharge targets. Here we have plotted the velocity profile. Then we have the fuel consumption. There you can see that for both optimizations, we used an identical fuel target. So fuel consumption is the same in the end. But 2 different battery targets was specified. So we start at 2 megajoules of battery energy. And in the blue case, we are charge sustained. So in the end, we still have 2 megajoules in the battery, whereas in the black case, we do a complete discharge. So in the end, we end up at 0 megajoules. What we already can see here regarding the boosting energy, the ES2K. So if we can discharge the battery in the black case, we end up at the 4 megajoules limit because more boosting with the MGU-K can be done if the battery can be discharged. In the blue case, where we have to end up here, we cannot boost as much. Regarding the recuperation, the limit set by the regulations is completely exploited in both cases. And then finally, when we look at lap time, so this is the time difference along the lap between the two solutions. The lap time is faster by 0.4 seconds in the end for the discharge case. So this is also intuitive. If I have more energy available and I can boost more with the electric motor, I will be faster along a lap. Next, we have velocity profile, and then gear shift trajectory or gear selection trajectory, and also the engine speed. And we can see that also the gear shift profile between the 2 solutions differs. And the question is, if we look here, you can see that in the blue case, so in the charge sustained case, the upshifts on the straights. So in the gray regions are corners and braking zones, and in white we have the straights. And the upshifts on the straights occur later in the charge sustained case. So here you can see we stay in 6th gear a little bit longer and then shift up. And here we stay in 7th gear until the very end of the straight, whereas for the black line, we upshift way earlier. Now, is there an intuition behind this? If we look at the power trajectories, we can see a possible explanation for this behavior, or why such a behavior is optimal. If you look, for instance, here, you can see that by staying in 7th gear in the blue case, and the car is still accelerating, the engine speed increases, and therefore the MGU-H recuperation is larger in magnitude than in the black case. So if we do the upshift here in the black case, then the engine speed drops and the MGU-H recuperation in magnitude, this is negative, in magnitude becomes smaller, whereas in the blue case, we recuperate more. You can see this on each straight basically, and marginally also here when we stay longer in In sixth gear, for instance, we also recuperate a bit more until we go up here. And as we have seen, this can be explained by the modeling trend. So as engine speed increases, MGU-H recuperation efficiency also goes up. So to conclude, if less battery energy is available in the blue case where we can't discharge the battery, the optimal solution will prioritize MGU-H recuperation over engine power. So even though engine power is slightly lower when we go to such high revolutions, we get more MGU-H recuperation which overall is beneficial for lap time. What we also see is that we have a very different behavior in terms of the MGU-K, so the other electric motor, and the MGU-K in the battery discharge case can boost much longer on the straight. So you can see that the cut occurs much later in the black case. We stay at high power for longer. And there's an associated lap time gain on each straight with this. And overall, this accumulates to quite a large difference together with other effects. Finally, when we look at the MGU-H recuperation, you can see that each time the wastegate opens, the MGU-H recuperation goes to 0 here at the beginning of the straights. As I said, this is due to the wastegate actuation. And here the interpretation is that when we can discharge the battery, so in the black case, the wastegate opens at the beginning of each straight, the MGU-H recuperation goes to 0, so drops drastically, but the engine power increases. And again, this gives us a small gain in lap time, and overall, this sums up. So, and this is only possible because we can discharge the battery by that much and are not do not rely on all this MGU-H recuperation. Next, we can look at the upshift engine speeds and see if there's any pattern in there. So, sorry. So here I've plotted the engine speed at which an upshift occurs for instance, when we go from third gear to fourth gear, so all the upshifts, and then for fourth gear to fifth gear, and so on, for the two cases considered, for the two battery targets. We can see that the upshifts from the lower gears are quite similar. So because these occur at the beginning of the straights where it's important to maximize propulsive power. And this is also the dominant component in the Hamiltonian. And therefore it's intuitive that here the upshift profiles are going to be quite similar. Whereas later on the straights, we can see that the pattern is quite different in the two cases. These upshifts occur later on the straights because we are in the higher gears. And here we have an important trade-off in the Hamiltonian between the kinetic energy and the energy consumption terms. And depending on the consumption parameter, so the battery target that we set, this can lead to very different results also in terms of the gear shifts. Finally, for the heuristic gear shift strategy, so now we look at how do the gear shifts occur in the real world. If you look at this onboard picture, so this is actually on the circuit of Bahrain, and you can see on the steering wheel, there are LEDs, and these light up as the driver goes through the ref range of the engine, and they tell the driver when to upshift. So this is akin to a threshold-based upshift rule. When the engine speed is higher than a certain threshold, upshift, do an upshift, so gear command +1. And we can incorporate such a rule in the heuristic scheme that we propose by replacing the gear shift optimization with this heuristic strategy and just computing the gear shift profile. So in each iteration, we get the velocity profile, and then we evaluate this rule and get the gear shift profile. And then we still iterate, and in the end, we get the optimal energy management strategies for the given heuristic gear shift strategy. So the energy management is still optimized, but the gear shift strategy was determined by a heuristic. Now we did a sweep of the upshift engine speed threshold for different battery targets, -2 megajoule, and then the charge sustaining case, and also a case where the battery is charged. And we plotted the lap time suboptimality for all these cases. The first thing that we notice is that the best threshold is yields a close to optimal lap time in the three cases considered. So if we fine-tune this threshold and choose it wisely, let's say, then this can be a very good approximation of the optimal solution. And the suboptimality is marginal. But a mismatch of less than 4%, so that's for usual upshift points, it's roughly 500 RPM. This can increase lap time in the order of 100 milliseconds. So that's a very large lap time difference in the Formula One world. Which brings me to the end of the talk. To summarize, we have seen an algorithm that optimizes the energy management and the gear shift strategies in a time-optimal fashion. And the velocity profile therein is also subject to optimization. And you have seen that we iterate also over the velocity profile. There are strong interconnections between the optimal energy management and the gear shifts because there are trade-offs in the power unit. And one example of this was the trade-off between engine power and MGU-H recuperation. Finally, we have seen that a fine-tuned heuristic rule can be a good approximation of the optimal solution. But if we deviate from the optimal threshold, the lap time losses can be quite large. As an outlook, this algorithm could be used as a design tool to optimize the gear ratios because you get the optimal energy management and the optimal gear shift strategies for each gear ratio set that you might want to analyze. And we plan to leverage the results as a benchmark for online controllers. This work was a collaboration with a large number of colleagues and under the supervision of Professor Honda. And if you are interested in reading more about it or finding out about all the details on this topic, make a bit of an advertisement. We have written a paper on this topic with the results presented, and this has been accepted and should appear shortly in Applied Energy Elsevier. So that's it from my side. If you have questions, yeah, please feel free to ask them now. Thank you.
Thank you very much, Paul, for the very cool talk. Are there questions from the audience?
Well, so you optimize the, for example, the gear shifts, right? But the gear ratios are fixed.
Yeah. Here the gear ratios were just like given parameters which we obtained from the.
Wouldn't you consider that, for example, the gear ratios could be part of the optimization?
Yep. This was actually what I tried to say as an outlook. We have already done investigations in this.
I missed that, sorry.
No problem. We have already done investigations in this direction, and basically Gregorius did those. And what he tried was combining this algorithm with particle swarm optimization, where you can then, with particle swarm optimization, try to optimize the gear ratios in a certain direction. Or certain gear ratios were optimized, the others were set to the fixed value, and then for each particle of the particle swarm optimization, we computed the optimal lap time with this tool, and we saw the trends, and this could help as a design tool for the gear ratio choice. So yeah, that's absolutely possible. Yeah.
Now, this is a question that you must ask in this day and age, right? So, have you thought at all about using some learning, some reinforcement learning, or something like that? And
so far, not on this project. We have used some, or my colleague Camilo Balerna in his research has used neural networks for the turbocharger modeling, but there it was more about having very precise nonlinear fits. Mm-hmm. So learning as such, learning techniques, we have not applied them yet. Yeah.
Are there any other questions?
So,
yes, I have a question.
Go ahead.
Paul, can you go back to slide 40?
Yeah.
Because what I noticed in the lap time plot, like after, at the third iteration, you're actually lower than after. Why don't you pick that
So a couple of comments here. You can see that after the first iteration, lap time decreases drastically. This is because of the initialization step. For the initialization, we choose a fixed engine speed, just as an initial value, to evaluate all the parameters. And in this case, it was an engine speed where the efficiency and so on was very bad. So then in the first iteration, you get a very high lap time, and then it comes down. If you would choose a very good engine speed where all the efficiencies and so on are very good, then you could even have a lower lap time. And now why it goes up a little bit here can be different effects. You can see that still the velocity profile has not fully converged. Also the gear shifts yet. So what is important to keep in mind, maybe let me go back 2 slides, is that you can have here mismatches between the velocity profile that comes out of the convex optimization and the one that you used to compute the engine speed dependent parameters. So it can occur that during the iteration, as we have seen here, you have not yet fully converged. Depending on how these interplay, the lap time could be slightly lower, simply because then the new velocity profile that you get is actually not in accordance with the engine speed dependent parameters that you used to compute it. And that's why it's important to monitor also these quantities and see that you also converge in the velocity profile and in the gear shifts, because otherwise you can have those mismatches interfering with your results. Does that answer your question?
Yes, yeah. So it is actually important that you have no mismatch or only a very small mismatch in velocity.
Exactly.
Okay.
For numerical reasons, it's never going to be perfect. That's a shortcoming of this method. One clearly has to say that. But we saw that, yeah, once the deviations go down to this low level, it's actually quite negligible. Yeah. But such an effect like this one can be explained by the nature of the algorithm. Yeah.
Okay, thanks.
Any other question?
Yeah, Paul, what if okay, so clearly, I mean, you want this optimization. You did this as an offline, right? Like a non-causal, try to, essentially get the best design in a sense, right? Things like that. How sensitive is the overall strategy to small perturbation? So, I'm just thinking of, so instead of now just going for a for a qualification lap or something like that, you're actually during the race, right? And there is somebody in front of you, or you need to make a pass or something else, right? So would you convert? How would you convert this from something that you do offline or like a non-causal to something that is more like a policy?
Yeah. So we have had already in the past a bit of look at this. So an optimal control policy was derived for this convexifiable model, let's call it like that. And it was shown to depend on these consumption co-state variables. And what we did in simulation, at least for covering disturbance scenarios, where you drift in the energy consumption during the race, was we acted with simple PI controllers on these co-state variables. And then you move the thresholds or the decision points in the optimal control policy, you move them around. And we have shown that in our simulations as well, on the benchmark simulation, where we could compare directly with the global optimal solution from the convex optimization routine, and also in a nonlinear simulation framework, just to verify that it's stabilizing the drift. We could show that the suboptimality was actually quite small. It was able to recover drifts. But if you don't do anything and you drive with your fixed policy, you can have very large drifts in the battery, and after 3 or 4 laps, your battery is completely depleted. And if you do it in the wrong way, or let's say you have a small drift in the battery, and we have seen that when you want to recharge quickly at the wrong location with the PI controllers, then you can have very large suboptimality. So maybe referring to your question, we want to have a look maybe in the future at other methods in order to have forecasts of the velocity profile and be able to handle these disturbances better. But so far it's optimal control policy based, and then we adjust the core state variables.
Yeah. Thank you.
Thank you.
All right, are there any other questions? If not, I think you know by now how to reach Pol for deeper questions. Pol, thank you very much. The talk was really interesting.
Thank you for the opportunity. And yeah, as Joelle said, if you have any questions, just drop me an email and I will happily respond. Thank you.
Thank you very much. See you all guys next week. Bye.
Bye-bye.